In quantum mechanics, things behave differently the moment they know you're watching. I'm going to do an experiment where light changes from this to this, all because it was being observed. But why do quantum objects care if they're being watched? This is the mystery that got me obsessed with quantum mechanics years ago. But I love this experiment because the three variations of it explain three crucial facts about measurements. And the third might even be a solution to the measurement problem itself. In the double slit experiment, you shine light on two very narrow slits, which I've represented here like this. And you can see that the light sort of spreads out and it goes through both slits. In fact, we know that this is what happens even with the laser because you can actually see it. If light is somehow wave-like, then this kind of makes sense because it's like saying the wave will spread out and then it will go through both of these slits and make new little waves. Eventually, these two little waves will spread and overlap. And as you can imagine, when two waves get in each other's way, they interfere with each other. And this is what causes the classic double slit pattern. This is a double slit, which hopefully you can see. And now I'm going to put the double slit in front of the laser and turn off the lights. Let's see what happens. And this is what the pattern looks like. And just as a side note, I never get over how beautiful this looks. Just crazy. And so now you get this double slit interference pattern, which looks like a whole bunch of little dots, right? Like there are these sort of bigger regions, and then in each of those regions, there's like little sub-regions as well. That's the double slit pattern. This all makes sense if you buy into the classical wave theory of light. But this isn't classical mechanics, this is quantum mechanics. And so many of my comments were like, shouldn't this be impossible? How can it be possible to see light going through both slits at the same time? And I understand why people are confused, because this seems to contradict one of the big ideas that I want to talk about in this video, which is that measurements cause collapse of the quantum state. So here's what that means. Light like this can be in a quantum superposition of doing multiple things at the same time. So for example, this light is in a superposition of going through the left slit and the right slit. And you can see why that's totally fine. It'll just lead to this overlap. But this rule says that this is fine as long as we don't ever try and find out whether the light went through the left or the right, because when we do, we cause it to collapse. So for example, if I was somehow to measure what the quantum state was doing by, let's say, looking at the light and seeing it going through the left slit, then I would collapse the state. And so it would have to only do one of these things. And let's say the right one might disappear. And so the rule says, when you look to see whether the light went left or right, then you collapse it to just going through one of the slits. So shouldn't that have happened when we were doing our experiment and looking at the way light was going? Well, don't worry, it's not actually a contradiction because of this. Suppose this is all the light coming out of each of these two slits before we measure it. And then we use the same technique that I did to see the light, which is to use a horrible carcinogenic smoke machine to make these little droplets of smoke here and there. And what this will do is when a bit of light hits one of these smoke particles, it will get deflected. And now that bit of light will no longer go through, but the rest of the light will go on sort of unaffected. So some little bits of light will deflect off these smoke particles and might even end up in the observer's eye or in the camera lens. And so that's why we can kind of overall see the path of this light. But it doesn't count as a measurement of most of the light, because you can see that most of the light goes completely unmeasured by the smoke particles because they never encounter any. And so that's why the smoke is actually not a good measurement of which way the light goes. But there has to be a cleverer way of figuring out whether the light went left or right and collapsing the state. And in fact, there is. Here's how we're going to do it. So when we imagine light as a wave, we're usually thinking of the wave sort of waving up and down, right? Like these are all the peaks of the wave, and they're sort of up and down. But actually, light can be a mixture of all kinds of directions of these waves. Like they could be waving left to right, they could be waving like this or like this. And this light is just going to be a huge jumble of all kinds of different directions. But what if we used this stuff to filter out the light? So let's say that we have some light coming in on some random direction here, but we only let through light that is oriented up and down, like this. So only this light would be able to go through. Or what if we turn the filter around and now it only would allow light going this way? So this light would go through, but nothing else. Well, we could do that and it wouldn't really do much for us. But here's the really clever bit. Why don't we do both? Why don't we put a filter in this direction over just the left slit and a filter in this direction just over the right slit? That means that light that makes it through the left slit has to be oriented like this, vertically. And light that makes it through the right slit has to be oriented like this, which is horizontal. What we've just done is we've marked these two slits. The light coming out of them are very different. And so if we want to know whether a bit of light is coming from the left slit or from the right slit, all we have to do is put a filter like this. Because a filter like this will only allow through vertical light, and it won't allow through this horizontal light. And so by measuring this polarization, we've also measured which direction the light went through, and we've collapsed it to only going through one, which is the left slit. If our rule that measuring the quantum state really causes it to collapse is true, then we should see that the light goes from being a double slit pattern to a single slit pattern. So if we can put these filters behind the two slits, then we'll have a way to test whether measurement collapse really happens. It was very, very finicky, but I finally got it to work. Here are the little filters that go behind the slits. So let's see if this really causes measurement collapse. This is the new pattern, and you can see that it actually looks quite different. Like the big patches are still basically where they were, but now there isn't these little lines in them. And just to see how different this actually looks, let's turn the camera around. You can see that there's basically only one beam that's really visible, which is the middle beam. The tiny little beams that you see in the double slit pattern are mostly gone. So observing this light really did change it. Just to double check that we really have collapsed this light into just going through one slit, I compared this pattern to what would happen if you did just have one slit to start off with. And you can see that they look very, very similar. The spacing of these bright bands is pretty much identical, which proves our hypothesis that observing the light really collapses it. But here's the really trippy bit. So this filter here is what allowed us to know that the light is going through the left slit. But what about if I just remove it? Here's what the light looks like with the filter, and here's what it looks like without. It's basically the same. It just looks a bit brighter without. So what on earth is going on? This second version of this experiment leads us to our second big idea for this video, and it's that measurement doesn't need a conscious observer. Measurement happens when information is leaked to the environment. To understand why this is true, let's look at our experiment again. So remember we said that this bit marks which way. What I mean by marked is the information about whether the light went left or right has now been transferred or copied onto something else. And in this case, it's the polarization of the light. So now the polarization of the light contains that information about which way the light went. And then that other filter we had, this was technically the measurement. When this is here, we know that the light that comes out must have gone through the left slit, and so we expect to see the single slit interference pattern, not the double slit one. So it'll look something like that, whereas the double slit one would look like this. Now, the remarkable thing that we found was that we didn't actually need this measurement. Even without it, we still only get the single slit interference pattern and not the double slit one. And it's because marking which way the light went is as bad as a measurement. One way to think about this is that information got leaked from the particle's position, so where it was, to its polarization. And this is a more general phenomena in quantum mechanics. Let's say we have an object that's in a quantum superposition of doing two different things, like our light, which was in a superposition of left and right. Then, let's say another particle comes along and marks the two options. For example, if the original particle was in state 1, the new one will lose energy. But if the original particle was in state 2, the new particle will gain some energy. So, the energy of this new particle now carries information about the original particle. And so that's what I mean by marking. Now let's say that that new particle just flies off with that information. What happens to our original object? It will look like it collapsed to doing one of those two things. The information leaking into the environment will look just like a measurement. This is called decoherence. Okay, but our story's not over yet because I want to show you the craziest variation on this experiment yet. So far we said that having these filters on top of the double slit marks which way the light goes, and since that information has leaked into the environment, it collapses the light to either going through the left slit or the right slit. But if that's true, then how do you explain this? Here we got the single slit pattern that we've gotten used to, but I can actually recover the double slit pattern by putting a filter in front of this, but not in the direction that we were doing before. If I put it at this 45-degree angle, you can see that I actually recover the double slit pattern. I just think this is insane. How crazy is that? You can see the double slit pattern just pop back out. It's even crazier when you look at it this direction, where this is the single slit pattern, which we expect because of our observation. And here is the filter. And look, it brings back the double slit pattern. The double slit only exists in front of the filter. But behind it, like, you can just see the single slit pattern. This is such a bizarre experiment. Yeah, look at that. How is it possible that if this is a measurement that collapses the light to only going one direction, that we're able to make it go through both directions later on by putting a filter in like this? Like, we're influencing whether the light went through both of the slits here by putting a filter in here. That's where the third, and I think most interesting lesson from this experiment comes in. Measurement collapse is an illusion. At least sometimes, and maybe always. So in the case of this experiment that we just did, which is called the quantum eraser, measurement collapse was an illusion. So here's what I mean. Originally, we said that just marking which way this light goes was enough to cause it to collapse. But let's say that it has in fact collapsed to just going left. Then it goes through some other filter, and then we end up with the double slit pattern. How is that possible if the light really had only gone through one of them? That would be like saying suddenly, after going through this other filter, not only does this light continue, but suddenly there's new light coming from the right slit, which is impossible if there wasn't any here. So we must have been wrong. There must have been some light still coming from the right slit at this point. But then how come without this filter, we didn't get a double slit pattern? We only got a single slit pattern. Well, what this shows is that without this other filter here, what happened on this side is just fake collapse. Or if you want to be technical about it, it's called subjective collapse. This sounds really bizarre, but it's actually not controversial at all. So what happens is when you mark which way the light goes, it doesn't actually collapse. Both bits of light are still there. They'll overlap in space, but even though this is happening, they're no longer able to affect each other. And remember, it was this interference that caused the double slit pattern. And now that that interference can't happen anymore, you just get the single slit interference pattern. Like I said, I know this sounds weird and it sounds a little bit mystical when I have to say it in English like this. But when you write down the mathematics of it, you kind of see why they're no longer allowed to interact. And it's all because of the fact that they're marked. Each one is marked in a separate way. And those two bits of light, now that they have this difference, aren't able to interact anymore. If you're interested in actually seeing that maths for yourself, then I've actually written it up and the link will be in the description. But if you're happy to accept that, then you'll understand why the 45-degree filter fixes everything. Remember, light that's coming through the left slit is vertical, and light that's coming through the right slit is horizontal. But if I put a 45-degree filter in between, what happens is that this light has a 50% chance of going through, and this light also has a 50% chance of going through. So after this 45-degree filter, firstly, both bits of light will now be oriented 45 degrees. So they'll both be oriented kind of like this. And any light that's gone through this filter is equally likely to have come from the left or from the right now, because both of them will have been polarized in the 45-degree direction. And so in a way, this filter undoes what this one did. It unmarks them. In other words, this filter has erased the information about which direction the light went. You can't just look at the polarization anymore to tell, did it go left or did it go right? And so everything is back to how it was. And you end up with the double slit pattern again. I love this experiment because it's a really tangible example of a more general thing in quantum mechanics. So you can have a particle that is in a superposition and then interacts with some other particle in a way that seems to make it collapse. And we might say that the second particle measured the first one. But then if you're able to get that second particle back and erase the information that was on it, you see that the first particle was still in a superposition, and now it acts like it was in a superposition the whole time. What I really like about that is that this is potentially a general story about what measurement really is in quantum mechanics. So replace that second particle with a measuring device or a human, whatever you want. And what we see is we have a quantum object, and when the person or the machine measures that object, it seems to cause that object to collapse. But it actually is recoverable. If there was a way to remove all of the information about what that particle was doing from your machine or from, your brain, the entire environment, every photon that interacted with that particle, then you're able to see that the particle was never actually collapsed at all. This whole thing of sort of fake collapse is called decoherence. And like I said, it's not controversial that decoherence happens sometimes. Like this example is a really great one of decoherence happening and then getting erased. So it's not controversial that this can happen. What is controversial is this the answer to the measurement problem? When we talk about measurement, is this what's always happening? It's so controversial because once you start saying that this is the solution to the measurement problem, what you mean is that every time you go and measure a quantum particle, there are two versions of you. One that sees the particle do one thing, and the other that sees the particle do the other thing. And both still exist. You will feel like you have collapsed to one of those, and the particle has collapsed to one of those. And every experiment that you try to do to get evidence about whether the particle has collapsed to going just one way or if it's still going both ways will show you, no, it's definitely collapsed. You'll only see the single slit interference pattern. But if you were able to somehow undo all of that, then you would see that actually there was no collapse at all. And really what happened was that you and the particle were in superposition, which I think is a very uncomfortable thought. This solution to the measurement problem is called the many worlds interpretation of quantum mechanics. And I think that at least mathematically, it's extremely nice. Because think about it, the maths going on here, we already know that it can happen, and it does happen in quantum mechanics. So you don't need to propose any new mechanism to explain measurement, unlike the traditional interpretations of quantum mechanics that do make measurement this special and very weird thing. In many worlds, it's completely natural. This is exactly what you would expect to happen if you take quantum mechanics very seriously. But I think that it does take a while to let that maths really sink in. So if you're interested, I have written up a bit more information about this experiment and how it generalizes a little bit. So the link's in the description. I'm also making a follow-up video about incorrect interpretations of the double slit experiment and this delayed choice quantum eraser experiment. So if you're interested, that should be here somewhere.